Hey guys, welcome back. So we're going to do some more practice in terms of doing Gibbs free energies. And actually, hold on just a second. I'm sorry. You can't see what I'm trying to share. Got the screen sharing set back up, but I didn't check to make sure it was actually showing what it was supposed to be showing. Okay, sorry. Always technical. Come on. Come on. Okay. So you'll probably notice that I have this pulled off to one side and I have my standard thermodynamic values over here. What we're going to be doing is calculating delta G, and we're going to be calculating delta G in two ways. So the first is using delta G naught F, which is going to be straight from the Gibbs free energy column, this third column, the standard thermodynamic values. Okay. The second thing that we're going to be doing is using delta H naught F and delta S naught F, the enthalpy and the entropy, to calculate that value at 45 degrees. Now, because our delta G values are at 25 degrees, I would not expect these to give me the same number. They won't, because they're not the same temperature. But I want you to see how we can use the data in either way to calculate delta G, okay? So a couple of these actually ask us to calculate the entropy, and then the rest of them will be for the free energy. So we're just going to calculate entropy for the first couple because that's what it asks for. So this slide, I'm going to have to pull over to the other side so that I can see it. Hopefully you guys have a copy of it because I'm going to need a lot more space to be able to show you these problems. So I'm going to add a new page here so that we can deal with that. And I have these questions over on another slide. So hopefully you can follow along with that slide. Okay. So, blank piece of paper. We are asked first to calculate the entropy for the formation of Ag2C2O4 from Ag, C, and O2. So I'm supposed to take Ag solid plus C solid plus O2 gas. And I want to make Ag2C2O4, which is a solid. Okay. And actually, I can show you that. It's right here. So this is the value that we're looking at, that Ag2C2O4, and you can see that it's a solid. Okay, so that's the material that we're going to make. Now, in order to do that, I need to have two Ags, I need to have two carbons, and I need to have two O2s. Okay, to make that one Ag2C2O4. Okay, awesome. So that's what I'm looking for. Now I need to get some values in order to be able to handle this. Now I'm going to go ahead and move this down a little bit because I didn't leave myself any space. This is fairly normal for me to do. I almost regret doing it as soon as I've done it. Since I want to do this calculation in two ways, I want to move this so that I can then do both of them. And what I'm going to do is write the delta G values above the line and then the delta S. So delta G up here, delta H, and then delta S. Or actually the S values that I will get from this table. Okay, so free energy on top, the H and the S below. So my free energy for that material is negative 584.0864. That's the value from that table. Now, if I go and look, and I'm actually going to pull those other values right now so that I don't have to deal with finding this again. So my enthalpy value for this is negative 673.2056. And of course, both of these are kilojoules. So kilojoules per mole for that one, kilojoules per mole for this one. And this one is joule per mole Kelvin. So there are different units on our delta, on our S values, or entropy values. So my entropy is 209.2. So that's my Ag2 C2O4. And I see my Ag solid is right here. My enthalpy value for that is 0. My entropy value for that is 42.55128. And my free energy is also 0. Okay, so that's that one. We'll go and look for carbon. And of course, it would be smarter if I actually search for it. Control F, C. Doesn't really help me though, because, well, it skips some of them. It doesn't skip enough. Oh, okay. So C, solid, and we're going to take graphite. And we're going to take graphite because that is how it actually appears in nature. And I can tell because my C has an enthalpy of 0 and a free energy of 0 for that particular species. And I see that my entropy is very small, 5.6944424. Okay. Let's go and find our O2, which is going to be similar. I would expect it to have a delta H, or an H value, an enthalpy, and a free energy that is 0. That's my expectation, because that is how it appears in nature. So I would expect that it would not have, wait, what the heck did I do? Oh, I do want O2. O2, right there, gas. Enthalpy is 0, free energy is 0. So again, I'm going to write 0 here, 0 here. And then my O2 gas is 205.0285552. Okay, so now I have all of the values that I would need to be able to do any of the calculations that we've talked about. Okay, so I can calculate delta G directly from the delta G values that I have, and that's an easy one, right? Because my delta G, not F, is equal to the sum of the stoichiometry for my products. Oh, sorry, stoichiometry times the delta H, not F, for my products, minus the sum times the stoichiometry of the delta H, not F, for my reactants. Cool, that's awesome. So that's my equation, sum of my delta H, not stoichiometry, times my delta G values. My delta G is right here, this 584.0864. So, and I only have 1 mole of negative 584.0864. And again, that's kilojoules per mole, minus the sum of the stoichiometry. Well, okay, 2 times 0 plus 2 times 0 plus 0. Okay, so that's what I'm subtracting from that. So obviously, the delta G value that I'm going to get is negative 584.0864. And that's in kilojoules because we're making it for 1 mole of this material. Okay, so my answer is in kilojoules. I've multiplied everything by the number of moles, so that's what I would expect. Okay, so that's one way. Now that's our direct delta G. Now the other way that I can calculate delta G is I know that delta G is equal to delta H minus T delta S. Okay, so I would need to calculate a delta H and a delta S for this. Now remember, our temperature, we have 45 degrees C, which when we do the conversion from degrees C to Kelvin, 273.15 plus 45 gives me 318.15. Okay, and that's in Kelvin. So let's calculate delta H value. So delta H, again, delta H F is going to be equal to sum of the stoichiometry of my Oh, and that should be, no, sorry. This should not be delta H. That should be delta G. I am so sorry. Delta G, not F. And delta G, not F. Reactants. This is delta H, F for my products. Minus the sum. Oh, it's the stoichiometry of the delta H, not F, for my reactants. Okay. So again, looking at my delta H line, the only thing that has a value is that product. So I have 1 mole of product and multiply that by the negative 6673.2056. I will then subtract 0 times 2 plus 0 times 2 plus 0. And that gives me a delta H of negative 673.2056. And again, that is in kilojoules for that. Okay, that's delta H. And when we want to talk about delta S, not F, is going to be the sum of the stoichiometry of the delta S, not F, for my products minus the sum of the stoichiometry times the delta S, not F, for my reactants. And this one is a little bit more complicated because none of these values are 0. None of my entropies will ever be 0. The other thing we have to remember is that this is in joules, not in kilojoules. So products minus reactants. So my S for my product is 209.2. And I'm leaving the units out. All right, this is joules per mole Kelvin, but I'm leaving the units out. I'm going to subtract the quantity of 2 times 42.5512. And actually, hold on, sorry. I want to make sure that it's very clear to you why I'm doing what I'm doing. Let me back up. So this is in joules per mole Kelvin. I multiply that by 1 mole. That's going to end up giving me joules per Kelvin as a unit. Okay. We then have 2 mole of that first Ag times the 42.55128 joules per mole Kelvin plus, and I'm going to keep this over here, 2 mole times 5.694424. 5.694424 joules per mole Kelvin plus 1 mole times that oxygen value. My oxygen value is 205.028552. 205.28552. Okay. Give me 2 seconds. I need to plug something in, otherwise it's going to die. We don't want death. Bad and difficult. Okay, that plugged in. Okay, so I can now do all of that happy math. Now I'm going to combine all the stuff on the product side first. So 2 times the 42.55128. That gives me 85.10256. I'm then going to add to that 2 times 5.694424 plus 205.028552. And that gives me a total on here 301.51996. And again, that's joules per Kelvin. So, and we end up with 209.2 joules per Kelvin. So 209.2 minus that answer that I just calculated, and that's going to give me negative 92.31996. And of course, that number makes sense to me. It passes my smell test because I'm going from 3 separate entities, one of which is a gas, to a single solid. So I would expect that to be less, there's less disorder there. Even though that molecule is bigger and therefore has more arrangements within it, that's not as big of a factor as having separate molecules. Okay, so that's the value that I calculate for delta S. Now, if I remember correctly, delta G, not F, or delta G, sorry, is equal to delta H minus T delta S. So delta G is going to equal the delta H that I calculated, which was this value right here, negative 673 right there. We're going to copy that. I'm going to put that down here. Minus that 318.15 Kelvin times the delta S, which is 209.2 joules per Kelvin. So when I do that simplification, I get 673.2056 kilojoules. And 318.15 times 209. Oh, no, wrong value. Sorry. I wrote this down wrong. I apologize. I copied the wrong number. 92.31996 joules per Kelvin. Now watch out for that because that's a fairly common thing to have happen is we don't necessarily get the right number when we have to use that number again. So I apologize for that. So once I get that plugged in there, that gives me minus, and it's 29371.5, but it's in joules. So I need to divide that by 1,000. So to get the conversion to kilojoules, and that gives me 29.37159527 kilojoules. Hooray! That's so exciting. Okay, now I can do that math. 673 negative 673.2056 minus that answer. And we end up adding that. So minus, and then this value is negative. So that ends up being adding that. So .2056 plus 29.37159527. And of course, that gives me negative 643 point. And I see that most of my numbers, looking at them, have 4 decimal places. Well, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. But that one only has 1. Okay. Come on. I'm going to leave it with 5 significant figures. And again, I'm not overly concerned about the sig figs at this point. And that's in kilojoules. So that's my negative 643.83. Okay, so I've done this calculation in 2 ways. They are not the same value, which I would not expect them to be. So we did the the direct addition method using the values from the table, and then we calculated delta H using the values in the table, and the delta S using the values in the table, and then we combine that using our delta G equals delta H minus T delta S. And remembering to do our conversion to Kelvin and make sure that they're both actually in kilojoules or joules. Doesn't matter which way you do it as long as they're the same. So that's what I'm looking at there. Now, I was actually only supposed to calculate the entropy for that, but there you go. Now I've done the whole thing. So calculating the entropy would have given me that negative 92.31996 joules per Kelvin. And of course, this is joules per Kelvin. Okay. So we've now done an entire set of these. I think I'm going to choose one more of these. And I think I'm going to choose formation of NH4F from HF gas plus NH3 gas to give me NH4F. Okay, so let's go find our NH4F. So NH4F is a solid as it appears in the table. So even though I may have wanted to look at something else, that's the only thing I have values for. So that's what I'm going to choose. And this time I'm going to go delta. Try and neaten things up a little. Delta G here, delta H here, and delta S there, which are not the order that they appear in the table. Those are delta H, delta S, and then delta G. And of course, units on each of these. Delta G is going to be in kilojoules per mole. Delta H is in kilojoules per mole. And delta S is in joules per Kelvin. Okay. So NH4F, delta G on that is negative 348.77824. The S on that is 71.964. Oh, wait, wrong place. Oops. Where'd it go? 71.9648. And then my delta H on that same thing is negative 463.96376. Okay, let's find our NH3, which is going to be this one right here. I can try and do this. Okay. NH3 gas, our delta G is negative 16.48496. Our delta H is going to be negative 46.10768. And our delta S is 192.33848. And then we can go find our HF. And our HF gas. I'm just going to scroll this to make it easier for me. Highlight our values there. So on my HF, my delta G is negative 273.2152. The delta H is negative 271.1232. And my S is 173.67784. Okay. So those are my values there. Awesome. So now I have all of my values. Cool. So let's do our delta G direct calculation first. I'm not going to rewrite the equation. I am hoping that by now you know that every time we do this, it's the sum of the stoichiometry times the value that we get from the table for all of our products. and then add all those together, and then subtract all of those reactants from that. Okay. So I have one product here. I make 1 mole. So I have 1 mole times the negative 348.77824 kilojoules per mole. I'm going to subtract from that this quantity, 1 mole times negative 273.2152. Yeah, that's 2152. Not sure what I wrote anymore, but that's what we're going with. Plus 1 mole times the negative 164.48496. Okay. So negative 273.2152. We're going to add to that the negative 164.48 496. And that's going to give me negative, simplifying here, negative 348.77824, and that's in kilojoules, because I've gotten rid of the mole by doing that multiplication, minus the negative 437.70016, which is the combination that I get from the two of those. So negative 348.77824 minus the answer that I just calculated, which gives me a positive 88.92192. Now, one of the things that I want to talk about, just you'll see that I mentioned that passes my smell test. And I usually say it when I get to S because I remember to do it there. But, heats of formation, it's harder for me to guess if it's going to be endothermic or exothermic for that. So I can't really say that makes sense to me. I have a value. This happens to be endothermic. The one I had for the last one, this value up here, wherever it went, this is exothermic. So it's giving off energy to the surroundings. This one has to take it in order for this to happen. So that's, and actually this is delta G. So this is not endothermic. So this means that this is non-spontaneous as written. So as it's written, we're not going to go and get this reaction to go forward. It just won't. What happens, on the other hand, is if we have NH4F, it will spontaneously decompose to give me NH3 and HF. Okay, that is favorable for this situation. And of course, if we reverse it, then we change the sign on that value. Okay, so it becomes negative and therefore it's spontaneous. Cool, awesome. Let's talk about what our delta H value would be for this. And again, we're talking products minus reactants. So negative 463.96376. And that's kilojoules per mole, and there's 1 mole. We'll subtract this quantity, 1 mole times the negative 271.1232 kilojoules per mole plus 1 mole times negative 46.10768 kilojoules per mole. And so here we end up with negative 463.96376, and that is in kilojoules. Again, because I had 1 mole, so that gives me just kilojoules. I'm going to subtract this whole quantity. So negative 271.1232 times 1 plus 1 times negative 46.10768. And that gives me negative 317.23088. Okay, and again, and that's kilojoules. So if I take the negative 463.96376 and I subtract the answer that I just calculated, that gives me negative 146.73288. So I can see that this is exothermic. So that is favorable. That's cool because there's no temperature dependence that goes with that. So it's exothermic. So that part is favorable. Now, when we talk about the delta S, I'm guessing that it's not going to be favorable. And so when we look at our values for delta S, we have 71.9. Actually, I'm just going to, because I can cheat. So when we do our delta S, we have our 1 mole times 71.9648 joules per mole Kelvin. And we're going to subtract this whole quantity of 1 mole times negative 146.7. Oh, not, sorry, wrong one. I'm looking at the wrong number again. 1 mole times 173.67784 plus 1 mole times 192.3384. Again, those are joules per mole Kelvin. So when I simplify this, I end up with 71.9648 joules per mole because we got rid of the Kelvin. And then we subtract 173.67784 plus 192.3384. 366.01624. And that's joules per mole. And that gives me a negative value. So 71.9648 minus that quantity that I just calculated. And that gives me negative 294.05144. So I can see, and that's joules per mole. I can see from looking at this that it's a negative value. That means it's not favorable for that to happen. And why would that be the case? Well, okay, again, I'm going from two species that are separate, both in the gas form, to one species that's a solid. So that is not a favorable change in my entropy. Okay, so the only time that this can be spontaneous is when my temperature is a small contributor to this. Okay, because that temperature has to be a small contributor to make this spontaneous. Now, can it happen? Yeah, it probably can, but let's, I mean, we could calculate the temperature at which it could become that, but right now we're going to calculate delta G. Delta G equals delta H minus T delta S. And the delta H that I calculated is negative 146.73288. And that was kilojoules per mole. And then my temperature, again, is the 318.15 Kelvin times the delta S, negative 294.05144 joules per mole. And of course, we're going to convert this so that we end up with an answer in kilojoules. Okay, awesome. So 318.15 times that answer that I calculated. And then we divide that by 1,000. And so we have the negative 146.73288 kilojoules per mole. We subtract from that the negative 93.55246564 kilojoules per mole. So negative 146.73288. Subtract what I calculated. And that gives me a negative 53.18041436. And that's kilojoules per mole. Now, when I look at this, I can see that delta G, even at that temperature, is still positive. Okay, so that S term has not become big enough to make it non-spontaneous. All right. So this is what we're talking about when we're talking about the values of delta G and delta H and delta S and how some of them are favorable, some of them are not favorable. And even when we have a situation where one is favorable and the other is not, we can get to a situation where it's no longer going to be a spontaneous process. Okay, so that's what we're looking at there. Now, hopefully that works for you. And that's two of those examples. I will go ahead and put the rest of them on D2L so that you can see the calculations that I've done. But again, it's going to be looking all of those values up in the table, doing this over and over and over again. You may notice that I was very, very careful with my signs, because one of the biggest mistakes that we usually find is that people were not careful with their signs. They lost a sign somewhere, and that changes the values that they see. That's a problem. One of the other things that you saw me do was to read the wrong numbers, and that happens too. So we need to make sure that we're reading it the way we need to be reading it, both from the table to the paper and from the paper to the new calculation that we're doing. So places where you can definitely go wrong, again, looking at your scratch work, I'll be able to see that. And that's, a minor mistake. You're not going to lose a ton of points for that, especially if you knew what you were doing. So everything else that you've done is correct. But that is something that we need to take into consideration. Okay. So hopefully you guys are good with that. I'm going to go ahead and I think I'm going to. So the next thing we're going to talk about is, yeah. We just did this. Apparently I have it twice. Okay, I'm sorry. I meant to do entropy, enthalpy, and then free energy, but I had you do all of that in the one slide. So sorry it was there twice. So the next thing we're going to talk about is how to estimate that temperature. I said that we could estimate it. So we're going to estimate it using this. I'm going to take a break and give you a little bit of a break here, and we'll get started again in a couple of minutes. All right. Thanks, guys.